Thanks. I'll begin with a prayer. Heavenly Father, we thank you again for this opportunity we just have to meet together and to study your creation. I just pray that you be glorified in what we do this day, Lord. In your name I pray. Amen. Okay, so I think I told you guys, I can't remember, what did I say at the end of class time? Did I say I would, what's that?
We're doing integration by parts.
Integration by parts, right. I still have a little bit of hyperbolic stuff to do. So we'll get to integration by parts in about 15 minutes or so. But I wanted to discuss why this formula is true. Sinh inverse of x is equal to the natural log of x plus the square root of 1 plus x squared. Now, you're taking the natural log of an algebraic expression. What's the domain of inverse hyperbolic sine? That's the same as asking the question, what's the range of hyperbolic sine, right? What's the range of hyperbolic sine? Yeah, the whole real line, right? So this formula, if it's going to be legit, we might hope that it's true for all real x. But you kind of worry a little bit here because x could be negative. It's like, am I taking the natural log of something negative? But why isn't that going to actually be a problem? What about the square root? What's it always larger than in magnitude? X, right. The magnitude of x is smaller than this. Right? So this quantity is always positive, despite the fact that it has a negative piece. It always loses to this root. Okay, so the formula at least makes sense. And then what Larson said is that, well, you can check. You can show that sinh inverse of x is equal to x and sinh inverse of sinh of x is equal to x. And, you know, if you show both of these equations are true, then that means that it actually is the inverse function, right? And he's not wrong, right? Not wrong. But there's a giant question that's just sitting there waiting to be answered, which is, where did the formula come from? Why natural log of x plus 1 plus x squared? Why, right? And he doesn't give you any indication, as far as I could tell in the book, why that's true. And I think it's something that is good for us to talk about and work out. So let's do that. So what we're going to do is we're going to call the thing we're interested in y. All right? So I'm saying y is inverse hyperbolic sine of x. Then what we have here is sinh of y is equal to x. But what was sinh? Right? It's 1/2 e to the y minus e to the minus y, by definition. And let's see here. Then what I'm going to do is multiply by 2, bring the x to the other side, so I got like e to the y. I guess I'll say minus 2x minus e to the minus y equals to 0, right? A little bit of algebra there. Now you just have to have a little bit of imagination. To solve this kind of equation for y, what you have to do is you multiply by y. Why do I multiply by y here? Why would I multiply by y? What would that do for us? Yeah. Oh, okay. I take that to mean that that would give us e to the y squared minus 2x e to the y minus 1, right? That's what you're saying. That's correct? Sure. Let's see here. I mean, anyway, I think many of you could do that, right? I mean, the harder question, the harder thing to say is, why would you multiply by, oh, goodness gracious, e to the y? Okay. I said, yeah, that'll happen. Let's see here. So multiply by e to the y. Why did I do that? Yeah.
You turned it into, I guess, a polynomial.
Turned it into a polynomial in what? Yeah. Got rid of the fraction. Also, yeah, exactly. So let's let lambda, if we let lambda equal e to the y, then what does this look like? This becomes what? Lambda squared, right? Minus 2x lambda minus 1. So this is a polynomial in lambda, right? It's a quadratic. So how do you solve quadratic equations? Factor or quadratic formula. I'll complete the square. You guys usually need practice with that. So I take half of this, which is x. I square it, right? Now, by writing this, lambda minus x squared, what does that do? It will reproduce lambda squared. It will reproduce minus 2x lambda. But it also has the side effect of adding x squared, right? So to be fair, I subtract x squared. All right? Now, what I've written so far, it's equal to these terms, right? Then there's still this extra minus 1 sitting there, so minus 1. So next step, lambda minus x quantity squared equals to x squared plus 1. Then we can take the square root of both sides, right? So we get what? We get that doesn't need to be there. We get lambda minus x is equal to plus or minus the square root of x squared plus 1. But that gives us lambda, which is, by the way, e to the y, is equal to x plus or minus the square root of x squared plus 1. You know, taking the square root of something squared brought into play this plus or minus, but is it real? I mean, do we really need plus or minus? Can we pick it? Can we make an informed decision on which sign we should keep here? Which one and why? Plus and why? Why do you say plus? I'm sorry? Why can't it be negative? How about because e to the y is positive, right? This is one of the fundamental features of the exponential function. So there you go. E to the y is x plus the square root of x squared plus 1. Solve for y. This gives us y, which, by the way, was inverse hyperbolic sine of x, right? Equals to the natural log of x plus the square root of x squared plus 1. And there you have it. That's why we have this formula. You can derive it with simple algebra. And the same is true of all the other, well, they may not be as simple. I mean, the one we did yesterday with the, we derived the inverse hyperbolic tangent formula yesterday. That one was actually a little bit easier than this. We didn't even have to do a quadratic equation. It just kind of fell out. I haven't worked through all of them, but the work is similar for all of these formulas that you are given in theorem 5.24 in Larson. Okay? These are sometimes useful. I mean, what's one use of it? Suppose you wanted to find the derivative of inverse hyperbolic sine. What is it? Did we work that out yesterday? I think we did cosh. Square root of 1. So I did work this out yesterday?
Yeah.
And what did we get?
1 over the square root of 1 plus x squared.
Did you 1 plus x squared? Or 1? Are we talking about inverse hyperbolic sine or inverse sine?
Inverse hyperbolic is plus.
Plus? That would make more sense to me on the basis that the domain here is all reals. It must be plus. It can't be minus. If it's minus, there's vertical asymptotes. I mean, there's like there's vertical tangents rather and the inverse hyperbolic sine at plus or minus 1 if there's a minus there, and that's just not true, right? Since it goes on, it behaves like an exponential divided by 2 either way. So it doesn't have anything so interesting in its graph. That must be the formula. But here's another way you could derive it. I mean, how did we derive it yesterday? You guys remember? Y equals this. We take sinh of y, get sinh of y equals x. We differentiate cos of y, dy dx equals 1. And so dy dx is 1 over cos y, but cos y is the square root of 1 plus sinh squared y, which was 1 plus x squared. Yeah. So I mean, we went through that implicit differentiation argument. But now, there's another way we could do it. If we have this, we could find the derivative of inverse hyperbolic sine. How could we do it? This is also a good exercise, right? You're like, beauty is in the eye of the beholder, sir. So here, you just got to differentiate this, right? Yeah. So it's 1 over what? X plus the square root of x squared plus 1. And then differentiate that, right? Chain rule. Yeah. If I didn't make a mistake. There is supposed to be a 2, but that 2 cancels with the other 2. It's a 2-2. Sorry, that's awful. I really want there to be like a minus or something. It doesn't, I mean, are these equal? I don't know, I'm kind of worried. So make a common denominator here, what do you got? Square root of x squared plus 1, right? Plus x divided by the square root of x squared plus 1. Oh, phew, math is still right. I was worried there for a second that we might do a derivation 2 different ways and get 2 different answers. I mean, after all, what's right or wrong, it's really in the eye of the beholder. We can agree to disagree, right? We all have our own truth, so forth and so on. No, sorry, math is not so sympathetic to these kinds of philosophies. There's kind of an objective answer once you start down a logical path. We can disagree about foundations of math, though. There is still a fuzziness. Just not in this class. There's still questions of style. I mean, is it inverse tangent? Is it atan? Is it arctan? There's stuff like that we can disagree about, but if you don't use my notation, you'll be wrong. So anyway, I'm just kidding. Mostly kidding. Kidding. I do have certain things I expect of you guys. I mean, you know, you notice that I really try very hard to, whenever I can, when there's thoughts, there's calculations which are linked, that's one step going to the next, I will stack equalities, right? I wouldn't, like, just do that and just, like, leave this floating somewhere. But you guys will do this. You'll like machine gun equations, or maybe shotgun's a better term, like one there, and then there's another one, and then there's another one here, and then like as the instructor, and then if it keeps going, some of you guys will like go back and start shooting them in here, and like it kind of like some kind of like snake, and then you got to like figure out what was the history of this calculation. Like these are not things that I'm willing to do in my grading, so I insist that you use notation somewhat similar to mine. And equations should be connected where they should be connected, and things shouldn't be floating. You should have equals or you should have equals, these sorts of things. I don't know why I'm telling you guys these things. I'm sorry. It's not interesting what I'm saying. Let's go on. So how many of you are interested in why we call them hyperbolic tangent and hyperbolic sine and You're probably wondering this, right? Like, so there's a variety of answers to that question. I mean, one answer to that would be, well, maybe we should say it's the circular cosine and it's the circular sine because sine and cosine are circular functions in the same sense that cosh and sinh are hyperbolic functions. So one good answer to that is given later in this course when we study parametric equations. Let me just flash forward. So let's do a little time travel to the later part of the course, okay? Because the easiest answer is there. So if you have f of x comma y equals to a constant, this is called a level curve. Some examples of level curves. For example, x squared plus y squared equals to r squared. This is a level curve. It also has a name that you already know and love. It is a circle centered at the origin, right, with radius r. But there are other things, like x squared minus y squared equals to 1. This is a hyperbola, right? The solution set to that's a hyperbola. So this is a circle. This is a hyperbola. And a parameterization of a level curve, what that is it's two functions. When you put x equal to a function of time and you put y equal to a function of time, then this gives us a parameterization of the level curve. So parameterized curve would be something like, parameterization looks like this. It's something like x of t, y of t, where if we plug in x of t and y of t into the level curve equation, we get back a constant. In other words, like in words, it's a formula for x as a function of time, and it's a formula for y as a function of time, such that when I plug it back into the equation, it works. So for the circle, we can just use x equals to r cosine t and y equals to r sine t. This is the usual parameterization counterclockwise of a circle. This makes sense because if you calculate x squared plus y squared, you get r squared cosine squared t plus r squared sine squared t. But you guys know what happens with sine squared plus cosine squared. You get 1, right? Factor out the r squared, and this just gives us back r squared. Hooray, it's a parameterization. See, it satisfies the defining equation for a circle when you plug it in. So for a hyperbola, if you put x equals to, let's see, is it cosh or sinh here? I don't remember. It depends on which kind of hyperbola I'm looking at. There's different ones. There's ones that open sideways, and there's ones that open up and down. Don't even get me started on the tilted ones. I mean, we don't have the technology for those in here. But how about this? Cosh t for x and sinh t for y. Is that going to work? Let's try it out. X squared minus y squared is equal to cosh squared t minus sinh squared t, which is, as we proved the other day, 1, right? So the hyperbolic sine and cosine parameterize hyperbolas. That's one reason they're called hyperbolic sine and hyperbolic cosine. They play the same role for hyperbolas that sine and cosine do for circles. So this is one good reason. Another interesting reason is that cosh and sinh are tied to hyperbolic geometry in the same way that sine and cosine are sort of tied to what we might call Euclidean geometry. A very interesting application of hyperbolic sine and cosine and all this is given by special relativity. Do you guys know what special relativity is? Show of hands, special relativity. No? Okay. I mean, I don't think that's usually part of the required high school education. That's fine. So what is special relativity? In the mid-19th century, we by then had a good understanding of classical mechanics, which is basically physics 231. Acceleration, velocity, net forces, mass times acceleration, this stuff, all right? In this way of thinking, if you're on a train and you throw a baseball forward, what's the speed of the baseball if you're watching from the outside the train and like just looking at it? What would it be? It would be the velocity of the train plus the velocity of the ball, right? So if you could imagine somehow having a flashlight on a train that was going at the speed of light, from this way of thinking, how fast should the light be going on the train that you're shooting the flashlight with? Twice the speed of light, right? This would be the so-called Galilean viewpoint, which is implicit within classical mechanics. But about the mid-19th century, Maxwell came along, and Maxwell added a term to the existing equations that studied electricity and magnetism. And this term which Maxwell added, Maxwell's corrections to Faraday's law, the mathematical consequence of that is the wave equation for electric and magnetic fields in a vacuum, or linear media, whatever. And basically what this equation says is that the speed of light is c. It's a constant that's just a consequence of the physical nature of space-time. So how do you get twice the speed of light for a moving train in that theory? It's not there. So it became mathematically clear that the electricity and magnetism Maxwell discovered was at odds. It was mathematically inconsistent with Newtonian mechanics. And there are a variety of hypotheses put forth at the end of the 19th century to try to fix this, the ether hypothesis, other things. The Michelson-Morley experiment was done to try to discover this ether, and it was a null result. And yeah.
How did he come to the conclusion that the speed of light is constant again?
Oh, because in electricity and magnetism, there's a wave equation for light. And it says that c is equal to 1 over the square root of mu naught epsilon naught. This is the permeability, that's the permittivity of free space. It has nothing to do with the reference frame. It's just property of space-time itself. So this invariance of the speed of light is kind of just built in to electricity and magnetism.
So we assume that it's constant?
No, I mean, we've done experiments. We discover laws of physics that govern electric and magnetic fields. A consequence of those laws is that the speed of light is the same in all frames of reference. But now, after that, Einstein comes along and he makes it an axiom for special relativity that the speed of light is constant in all reference frames. So it kind of depends on who you're listening to at the starting point of the talk. Yeah. Anyway, special relativity, introduced to sort of reconcile this, said, you know what, Maxwell's right, electricity and magnetism is legit. It's the classical mechanics that's got to go. So what Einstein said was that there's this interesting relation between space and time that's governed by what's called special relativity. And it changes the rules of velocity addition. It's no longer true what our common sense tells us. If I throw a ball at half the speed of light on a train that's going half the speed of light, that does not mean the ball is going at the speed of light. It's less. So it modifies the rules of velocity addition. And it basically puts a cosmic speed limit that massive things can't go the speed of light or faster. The equations become imaginary in that context. Now, anyway, this is not physics 2. I mean, I'm sorry, this is not calculus 2. I'm so sorry, I'm wasting your time. But an example in this world is also having to do with this hyperbolic tangent of phi is equal to beta. This is equal to v over c. Phi is called the rapidity. And so this, it turns out, is useful for understanding velocity addition and special relativity if you take a class in it. Don't look too hard at our course catalog, it's not there. But if, wherever 10 or more are gathered together and ask me nicely, I would certainly be willing to try to make that course happen for you. And I think the same is true of Dr. Skambordis, but you probably should think about a creative bribe. Let's see here. I'm not sure what it would take to get Dr. Skambordis to do that. You would have to convince him that you were very interested. Well, that's true for me too. Let's see here. So go take physics 1, take physics 2, pass it, pass them. You don't have to pass it the first time, but pass it eventually. Show enthusiasm. And No, let's be optimistic. You're going to pass it the first time. And then come talk to me about it. Anyway, or Dr. Skimbordas, he knows lots about this stuff too. What I'm trying to get at here is, so this is 1 minus beta squared, right? So this is an identity. This is the identity for hyperbolic tangent, which is why I'm even showing you this example, really, just to showcase some of the math we've already done. And so 1 minus beta squared is equal to that. So that means that cosh phi is what? 1 over the square root of 1 minus beta squared. Traditionally, this quantity is known as the gamma factor. And it's kind of neat, the way the math works out. This is gamma. A lot of times to do special relativity, you just take the known formula from classical mechanics and multiply by gamma. There's a few things that kind of work out like that. It's an interesting thing. See what this only makes sense. What's the domain of this? You need that. The absolute value of beta is what? Less than 1, aka the absolute value of v over c less than 1. So it says that the absolute value of the velocity is less than c. Now, c is the speed of light. I didn't tell you that yet, but I should tell you. Sorry. So c is the speed of light. And that equation has built into it that it only makes sense if the velocity has a magnitude which is not larger than the speed of light. So cosh phi is gamma. What's sinh phi if cosh phi is gamma? Isn't it tanh times cosh? Is that right? Does that make sense? If tanh is sinh over cosh, then tanh times cosh is sinh, right? But this is beta, and this is gamma. So there you have it. These are sort of the fundamental relations here. Cosh of phi is gamma, sinh of phi is gamma beta. And I will stop this brief tour into the unknown in just a moment. This may demotivate you or motivate you to think more about cosh and sinh. I don't know. It depends on who you are and how you. Does physics excite you, or does it demoralize you, or I don't know, somewhere in between. But here's the deal. These guys, so with sine theta and cosine theta in this little 2 by 2 matrix, this gives us what's called a rotation in plane. So rotation in the plane is given by, this will mix x and y and rotate x and y, right? The corresponding matrix with cosh and sinh in the same pattern, this actually is a velocity transformation in space-time. So cosh and sinh play the role of the rotating factors in some sense in space-time. They play the same role as sine and cosine do for regular rotations, for when we mix space and time together in these new interesting things allowed by special relativity. This is the matrix of what's called a Lorentz transformation. And finally, one more fun fact, and I promise I will stop talking about physics, unless you want me to say more, which is that you guys have been told E is equal to what? MC squared. That's a lie. So E is actually equal to gamma MC squared. That's the true relativistic energy, where M is the rest mass. This gamma, if you put V, what happens if you put V equals to 0 into the gamma formula? Or V equal to 0 is beta equal to 0. So gamma's 1, right? Yeah. So V equals 0. If you put V equal to 0, you should basically recover regular mechanics from special relativity. And so we'll come back to this formula later when we get to power series. I have a little bit more to say about this, so that's all I wanted to say for now. But yeah.
Is that the expanded formula up there? Is that like the sense expanded formula, or is there a more expanded formula?
This one?
I mean, I figured I'd ask. I always wondered. Because I was told there was an expanded formula.
There is, but we do not have the technology to expand it just yet. I will come back to it. I will resist the urge to answer your question right now. There's this good rule of like marketing, you should always leave them wanting more or something. I'm not really a marketer, but I've heard this, I don't know. I mean, I heard in orientation that, that your generation Z doesn't like things that are hard. Now, I told you my disdain for the whole idea of generations and thinking about people as members of generations, but if I did trust this advice at all, what I just did is crazy, right? Like, why would I do this? This looks awful, right? And I'm not actually testing on it. I'm just trying to show you another place where caution cinch are interesting and important. When I took special relativity at NC State, I declared my physics major as like my second semester at State or something, my third year in college. The professor started talking about caution cinch. And I looked at my friend Paul. I commonly call him Crazy Paul because he's crazy. I was like, what's caution cinch? We went to the professor after class. We're like, what are caution cinch? And he looked so sad because he then realized that we no longer talked about caution cinch at calculus at NC State at that point. So it is not healthy to not talk about caution cinch in the calculus sequence. It's the other half of a story. To not talk about caution cinch is just to tell half the story of calculus. There's so much more that you see when you also include caution cinch in the discussion. You'll see. All right. Enough about hyperbolic stuff for the moment. Any questions about anything? No. I wish we had a course in special relativity here. We don't at the moment. We used to, but then our physics minor got axed in the early 90s and we haven't gotten it back yet. All right, so something that will seem much easier to you guys. You're like, music to my ears. Integration by parts. Now, this is section 8.2 in your text, I believe. And you might notice there's also a section 8.1. I'm not saying section 8.1 is not important. In fact, I probably should take a minute and give section 8.1 its due comment. Because we're going to spend the next, I don't know, week, 2 weeks or so studying integration techniques, right? So the foundation of all these techniques is that you know basic integrals, right? If you don't know the basic integrals, then you can't do these techniques because you're trying to build your house on sand, you know? So let's just make a laundry list of the integrals we already know, okay? I'll start out small. Integral of x to the n dx is what? Over n plus 1. Plus a constant, I know. And how about the integral of dx over x? Natural log the absolute value of x plus a constant. Very good. I can't get you guys. Now this, of course, has some, what's that? Oh. This has some fine print. N not equal to minus 1, right? Because what happens when n equals minus 1, you get the log. All right, fine. We got sine, we got cosine, we got cosh, we got sinh. Do I need to write them again? Fine. Integral of cosine of x dx is? Integral of sine x dx is? Sine of x plus c. Sine? Negative cosine. All right. Of course, we also have the hyperbolic analog of these guys, right? I'm starting to feel like I'm never going to start integration by parts. All right, I'm going to keep going. It's important to give this list. Now here's the one you guys, here's the one that'll get you guys. And this always makes me, like this usually happens in differential equations. I give some problem where basically you end up facing this integral, right? And then they start trying to do u substitution. They start trying to do integration by parts. They start doing all kinds of stuff to try to do this integral. But it's just tangent x, right? This is a basic integral. I mean, this is like the first story. You know, I mean, there's no work. You need an education. It's educated guessing. You know that the derivative of tangent is secant squared, so that's it, right? Likewise, the integral of secant tangent is secant, right? And we've picked up a few more kind of interesting ones along the way here if you didn't know them already, like this one, right? Right. I mean, there's about 20 that we could write here, right? You go down the list of all the basic derivatives we found for inverse hyperbolic functions, and you know, there's also like cosecant squared. That's a good starting list. What's the other one that comes up a lot? This is important, of course, right? Right. Now, what the next thing, of course, we learn is u substitution, right? This might also be important. If we have a to the x dx is what? So we do 1 over the log if we have a more, you know, maybe we have a 2 to the x instead of e to the x or something. We have to divide by log 2. Past this, there's u substitution, right? Okay. All right. Integration by parts then. So we need to know these basic things. Otherwise, we get into trouble. We'll try to work harder than we need to if we don't know these, right? That's the thing. So what's the problem in integration? Let me do an example. Integral of x e to the x dx. So how should we calculate the integral of this? Is the question. Yeah? So here's the basic idea. If we take d dx, right, of x e to the x, what does that give us? And we get e to the x plus what? Plus x e to the x, right? So if you look at that, we can take this, right? And we can trade it for what? The total derivative of x e to the x, right? Minus e to the x. Why would we do that? What's the integral of a total derivative? Right. So this gives us x e to the x, right? And then minus the integral of e to the x dx, but what's that? Right. So how did I do this integral? I used the product rule, right? I used insight from the product rule to rewrite the integrand as a difference of related things, which I was able to integrate. This is basically the idea of integration by parts. Now, in practice, we don't do problems like I just did example 1. All right? We develop a convenient notation which we run our logic through, u and v. So I'm now going to derive the standard formula, and I'll redo example 1 in u and v notation here in just a minute. But I think it's healthy just to look at an example free of the u-v notation, which is just a convenient mnemonic for the idea. So here's the usual notation. We do something like uv. If we take the derivative with respect to x of u times v, this gives us du dx times v plus u times dv dx. Right? Consequently, the integral of u dv dx, right, will be equal to the integral of what? Of ddx of u times v minus du dx times v, all dx. Now, this is probably not the formula that you remember if you've studied integration by parts in high school, right? Like, this is not what you wrote down, is it? If you remember. What did we write down? I'm actually a high school dropout, so I shouldn't talk. U dv equals, what's the integral of ddx of uv? It's uv again, right? V du. So what's going on here? What's this notation? We're actually making a u and a v substitution. We're using the u substitution notation to change the measure of the integral from x to v, or from x to u. You can look at it in terms of like the dx is canceling, or the dx is canceling over here to give you v du, or u dv. So this is, you guys recognize this? You should recognize this, some of you. Here you go. This is the standard integration by parts template, let's say. So to do integration by parts, we need to identify a u and also a dv, right? So here's the algorithm. See the integral as the integral of u dv, identifying u and dv, right? This, whatever this is, probably needs to be able to what? Integrate it, right? I mean, if you can't integrate the dv, you can't actually put the template into action, right? If you can't integrate, v is the integral of dv, right? So how do you even come up with this unless you can integrate the dv? You know, this is something to look at. Okay, so I can talk about these generalities, but they only really sink in when we do examples after examples after examples. Let's do it. Let's do it. Example 1, tilde. Okay, same example, but with the boxed template. All right, integral x e to the x dx. So I got to choose a u and I got to choose a dv if it's going to work, right? So I'll make this dv, I'll make this u. And I usually like to write my choices off to the side. I say, okay, so u equals x, and dv is equal to e to the x dx. So if u is equal to x, then du is dx, right? And if v is equal to e to the x dx, that means v is what? E to the x, very good, yeah. See that sideboard knowledge is coming in again, I know. So here we go, I'll write down the template, the blank template, uv minus integral of v du, just to keep me honest. And then I'll put it in. So that's x, my v is e to the x, minus the integral of e to the x dx. The logic behind this is just what I showed you in example 1. It's just using the product rule in a crafty way, right? And there you go. We're back where back where I got to just a second ago. X e to the x minus e to the x plus a constant. There you have it. All right, so we're done. Next topic. Oh, just kidding. I think we still have some work to do on this one, yeah? Okay. What's another good example? And before I go on, though, I should just have questions. You guys usually have questions after I do about 3 of these examples. So let me bide my time here. Example 2, integral of inverse sine of x dx. Now, I mean, we kind of only have one option here. We cannot make the inverse sine the dv, part of the dv, right? Because we don't know how to integrate inverse sine. That's kind of the whole question. So it's almost inescapable. You have to make the u here the inverse sine, right? Which means the dx has to be dv. So, you know, there's a couple big things to do here. Well, number one is to identify that we're actually facing an integration by parts problem, right? How do you figure that out? You see a bunch of examples and you do homework. It comes from experience. What? Someone's texting me. Annoying. Really? Then the second thing is, once you've identified that's integration by parts, you still have the trouble of, what do you make the u, right? So how do we figure this out? I mean, you're not going to like my answer. Mostly practice. There is a meaningless algorithm that I will share with you that will help you choose the u. It was told to me by students. I didn't make it up. I think mathematically it's invalid. But it helps students, so I'll tell you. Just like I give my kids candy, even though I spent $3,000 on a dentist last year. Let's see here. Okay, so u is inverse sine of x. My dv is dx. Great. Now, I'll do the easy part. V equals x. Haha. Now, what's du? You guys learn or remember, or you're like, I knew that last semester. You didn't teach me anything. All right, 1 minus x squared, fine. Be that way. I'll allow it. Did I get it right? It's 1 minus x squared? Okay. Okay, so blank template. uv minus integral of v du. This step to me is kind of like training wheels. Eventually I take it off. But if I'm not careful and I'm sleepy and I take that step off, I'll do it wrong. So, I mean, this is kind of a dumb step, but it does help you stay on the straight and narrow, right? Okay, so uv here is x inverse sine of x. And then we have minus the integral of x dx over the square root of 1 minus x squared. Aha! You're like, but that's still a not so nice integral. But you should look harder at it. What is that integral? How can we do this one? Right. Since it's the second u substitution, it will be the w. Let w equal what? X squared. X squared. Yeah, you know, you guys who did x squared, that's okay. It would still work out for you, but it's lazier to let w equal 1 minus x squared. So let's be lazy. Because then dw is minus 2x dx. Yeah, so this is actually x inverse sine of x plus 1/2 integral of du over square root of u. Oh, I should have left that 2 on the inside, because then it would have been quite manifest that this is x inverse sine of x plus the square root of u plus a constant. Did I say u? I meant w. Sorry about that. I try not to use u again because I already used it in a different, different way. So just to make sure I don't confuse myself, and maybe I go away and look at that exciting text on my phone and come back and I forgot which one was u, and then it's all over. Anyway, so here we go. This is the answer. So apparently integration by parts maybe is useful for finding integrals of inverse functions, right? Hey, what's another inverse function that we know that we don't know an integral of yet? Maybe you don't know. Maybe you don't remember. What's the integral of log x? No. The integral of 1 over x is log x. See, I got you there. Yeah. I shouldn't even, no. How's there this debate? Should I actually write down common mistakes you guys make? See, because sometimes if I do that, I feel like it's then a self-fulfilling prophecy that you're going to make that mistake. Am I the reason the mistake happened then after that point? No? All right. So this is a very popular mistake. Whatever's down here, whatever it is, answer. No. It's not so simple. This is good for x. X, not f of x. But this is a very common and wrong belief, although not as painful to me as this one. Oh, who am I kidding? The person who does this won't even write dx. Let's just make it maximally wrong. What's the harm of not writing dx in the integral? It's exactly the sort of thing that could cause you to forget that you need to make this kind of step in your technique. Stuff happens with the dx computationally. If you get in the habit of not writing dx on integrals, I will get in the habit of taking all your points away. So there you go. So that's my encouragement to you. Sorry, I should find better ways of being encouraging. But anyway, these are very popular but very wrong mistakes, yeah. But I feel like I shouldn't write those because now you're going to be like, but you said that's how to do it. And like, no. Bad. Okay. So here, to me, this is the same example as example 2. Because I just make the inverse function u, I make the dx dv, so I do uv minus integral of v du. And here, u is, so it's x ln x minus the integral of v. What's v? V is x. What's du? It's dx over x, right? The x's cancel, and we get x ln x minus x plus a constant. So there's the integral of log. Let me do a slightly scarier one. Let's see how much time do I have? Uh-oh. This person I actually have to listen to. When you leave school. That's it? When you leave school. I don't know what that means. Oh, it must be the other text must have the exciting thing in it. Okay, sorry, I get distracted here. Oh, see, now I'm going to get comments on the YouTube. It's very unprofessional to look at your phone while teaching. It's like, what am I supposed to say? You got me. You probably should fire me now. Let's see here. Where was I? Example 4. I wanted to show you one more here. How about integral of something like x? No. I want something a little bit different. E to the x cosine of x dx. These always throw people for a fit. So, well, I don't know, there's different choices here, but I'll make this dv, and I'll make that u. I'm going to put a 1 on them, because I know where I'm going. So u1 is e to the x, dv1 cosine x dx, all right? So what's du1? What's v1? Integral of cosine was, what did we say? Sine, right? So sine x. Okay, so we got e to the x, sine x, right? And then minus what? Minus the integral of sine x, e to the x dx. Oh, man. It's kind of more of the same noise, isn't it? But what you do is you just, dust yourself off and try again. And so here I'll just say, okay, well, we'll kind of do the same thing. I'll just put the sine x and the dx together. I'll make a dv2 equal to sine x dx. And so v2 would be minus cosine, right? And I'll make my, my u2 e to the x. So my du2 will be e to the x dx. So I just integration by parts again. All right. Now here's where you got to be careful. This minus distributes to everything in the template for the second integration by parts. Right? Now put it, let's, put it in. What we got? We got e to the x, sine of x, minus, what's u2? u2 was e to the x. Minus and minus gives me plus cosine x, yeah? And then plus the integral of v2, which was minus cosine of x. And du2 is, e to the x dx, yeah? Let me rewrite this just a bit. This is e to the x times sine of x plus cosine of x minus the integral of e to the x cosine of x dx. So you're like, well, that was pointless. I mean, we just got back where we started again, right? You'd be right if we actually got back where we started, but we didn't, did we? You notice there's a critical difference between the initial expression and the final expression. If I call the initial expression I for integral, this is what? This is minus I. What are we trying to find? I. So we have I equals to e to the x sine of x plus cosine of x minus I. Solve for I. Right, so I is equal to 1/2 e to the x times the sine of x plus cosine of x, and then of course we have